So our next speaker is Gurindar Sohi. He's from the University of Wisconsin. And if you go to a computer architecture conference, Guri is very easy to spot. He has this presence and command until Yale walks in at 2. So today we'll get a little demonstration, I hope.
Okay, do we have a charger just in case?
I will hook you up.
I like a little redundancy.
Make sure we have enough time for you.
Oh, I guess you saw the title. That's why you guys are laughing. Well, thank you, everybody. It's a pleasure to be here at this very momentous occasion. Yale's the reason why I ended up at Wisconsin and not at UT, by the way. But that's the story for some other time. So about 7 or 8 years ago, I got invited to give a distinguished lecture at UCLA. And after the talk, Dave Reynolds comes up to me and says, "That is a great talk. Just promise me not to give talks in 10 years. And I said, why? He said, you know, when people like you come at your age, you give these great talks about how things are going to be in the future. But, you know, when people who are older come, it's always about reminiscing about the past." So since then, I decided that I need to get that transition smooth. So I'm going to spend 2/3 of the time reminiscing about the past and only a little about the future in some sense. Okay, so it's important to, again, reminisce and try and see where we've come from, and then we can talk about where we are likely going. And so where have we come from? Okay, where we come from since Yale was 45 was we've been going at performance, performance, performance. That was our main goal. And, you know, there were lots of, at times people would say, hey, you know, let's get the software people involved and so on like that. And, you know, the lesson you learn, and we hit on it multiple times, is no, the software guys don't care what you do as long as you give them faster or more efficient processors. They don't want to change anything to do. So we got continuous increase in performance without putting any demands on the software. And there were lots and lots of innovations under the hood. For example, the big MF, multifunctional predictor, that Yale Patt would talk about repeatedly. You know, many others, but the key point was they were all under the hood. And one of the key enabling techniques that allowed everything to be under the hood was the notion of a sequential appearance and precise interrupts. And this is a lesson that I learned from Mike Flynn many years ago. And he was telling us about the history of the 36091 project which he managed. And the lack of precise interrupts made it so buggy you couldn't get anything to work right. And that's what sort of put back out-of-order execution for quite a while until we figured out how to combine precise interrupts with out-of-order execution. Okay, so we did all that, and then once we had some of our basic stuff, then we sort of tried to put more and more on the core, ostensibly to do stuff better. So this sort of reminds me of Yale again, is one of the first papers of Yale's Patt's I read with Yale and a few students, and the figures were all hand-drawn by Yale. Okay, so Yale figured out that these student units, Shabanow and Hu and Melvin, it was more efficient for Yale to draw the figures rather than have these student units draw the figure for him, for example. Okay, and then many years later, Yale, would keep drawing these handwritten slides, and one day he asked me, Guri, should I start using PowerPoint? And I said, yes, Yale, it's going to improve your efficiency. Learn PowerPoint. So Yale learned PowerPoint to improve his efficiency, ostensibly. okay? And we'll see whether that worked out right or not. And using the same argument, what we've been doing is dumping all this stuff on processing cores. So we put in MMX, others put in vectors, and now you're having all these other things you put on cores, ostensibly to improve their efficiency. And you can actually justify it because it's an incremental cost. Okay. So now if you have quote-unquote a general purpose core, it is a catch-all for everything. Okay. It can do everything that you might imagine you want it to do. And so it's good for everything, but it's not the most efficient for any. And what happened recently, in the last 10 years or so, is efficiency became important. Okay? And so when efficiency becomes important, then you start looking at alternative solutions that are more efficient, whatever your metric is. So it's important to keep in mind that eventually you can do anything in hardware you want, but unless somebody buys it and puts software on top of it, it's no good. So let's try and figure out what's happened in the software world. In the good old days, you had only few applications and few customers. So you could go to your customer and say, hey, I'll work with you changing your software to do my new feature, all is good. And when we moved to the PC world, we had shrink-wrapped software, lots and lots of customers, okay? But still, the applications were few. I don't know how many, maybe tens or maybe less than 100 applications you could buy that would run on your PC. So those, those vendors could change their software in some way and spread it out, and you could then convince them to use your whatever little architectural widget you wanted to add, and all was good. Okay? And now what has happened is software is lots and lots of different people writing software, millions of applications, it's all over, and frankly, most of them do not care about what little widget you're going to give them, because to them, efficiency is not at all important. Okay? Ease of software construction is what's important. So when everything was under the hood, all was good. Software didn't have anything to worry about. And then the multi-core era came around. And what happened with this multi-core era is, companies like Intel or Reliance are going to have software to use the multi-core processors. Otherwise, it's, nothing's going to happen. They aren't going to be selling more processors. So, everybody went on the bandwagon, parallel programming everywhere. So, companies put in money, parallel programming, this, that, and we, first course and everything is going to be parallel programming and so on. Okay. The software people sitting down there and figuring, well, gee, you're going to make me change my software? If I'm going to do that, why should I use your stuff? Why should I not use this other little piece of esoteric hardware that may be give me more efficiency? Okay? And so, if I'm going to bite the bullet, might as well start using GPUs. And that's what happened. So, software is mostly going to avoid difficulty, people writing the app, and there are so many of them now, they're all over. And even if it's inefficient, convenience is what they're going to embrace. Okay. So what are some of the important lessons, takeaway lessons? Initially, when I have a small number of transistors, I'm going to try and, I can only build one core. I'm going to try and do whatever I can on top of the core because the cost is incremental. But how much I'm going to get from it is going to keep decreasing. And when I have many more resources, I can do everything. Like when I was in India, you went everywhere on a bicycle. Okay, well, when you can get a car, you start going places in a car if it makes more sense to go places in a car. Relative importance of special techniques diminishes over time. And Convenience is the key to software proliferation. Furthermore, it's the mass volumes that are going to drive the end result. Okay, so, you know, whatever you can sell hundreds of millions of, that's what you want to try and go after, and then build other stuff on top of that. Okay. So, what is the future going to look like? Well, I want to separate out, you know, what future academic research I think is going to look like, and then what products likely going to look like. So for academic, if you open up ISCA 7-8 years from now, here's what I expect to see. So you'll have general purpose app processing units. So, you know, everybody's writing apps, so we'll come up with some little app processing unit, and we'll make it general purpose, okay? Then we're going to have what I generically call XY DRAM. Okay, so, you know, this is sort of borrowed from the theory people. They had this PRAM model 30 years ago, 35 years ago. And then everybody had their own variant on that PRAM model. So they had one-letter prefixes to PRAM. And then the one-letter prefixes ran out, so they started having more than one-letter prefixes to PRAM. So we're going to have, you know, XY DRAMs. Then we're going to have 4D integration of those heterogeneous XY DRAMs. And what do I mean by 4D integration? Okay, it's like you're going to have the 3D layers, and they'll have some kind of inductive coupling, and you're going to move them around to dissipate heat. So at different times, the latencies will be different. So, you know, you're going to have dynamically varying latencies, and so you're going to have completely revisit cache design and everything else, okay, with 4D integration with GPAPUs. So that's what the ISCA papers are going to be about. But the real world is going to be something else, okay? So the real world is going to be, again, everything is going to be energy efficiency. So the challenge then is, how are we going to use more transistors to save energy? Okay, that's sort of like the conundrum over there. Okay, how are we going to use more transistors to save energy? And how is software going to change? I don't expect it to change much at all. You're going to have to keep doing everything under the hood, if you will. Okay, convenience, again, is the most important thing that software is going to be interested in. Okay, so we're going to have basically, you know, all sorts of innovations in every little aspect of the hardware. Okay. So we are going to have novel uniprocessor cores, and what they might, you know, might look like, we'll talk a little bit in just a while. And of course, you're going to try and do stuff on the device end to try and get lower and lower energy usage. And, you know, probably pushing the limit so you become have frequent errors. So errors are not the exception, but they are the norm. Okay, just like, you know, you don't need to be afraid of errors in a sense. You know, just like you don't need to be afraid of a branch misprediction, for example. Okay, and then you know, what you're going to do is you're going to have these customized computation energy reducers. You know, I don't like to call them accelerators, but accelerator means it's doing something fast, whereas what you are likely to be doing is going to be doing it with low energy, may or may not be fast. And, you know, going back to how is, you know, how is software going to use this diverse hardware? You know, when we were talking a lot about multi-core chips, and, you know, the standard mantra was, hey, you know, all this parallelism is going to be done in a library on multiple CPUs. And, you know, if you believe in that, then, you know, the question really comes up is, why should I do it on multiple CPUs? Why should I not use the same ideas to try and run that code on customized hardware, if you will? Okay, so now, going back to Yale and PowerPoint, okay. After a while of using PowerPoint, one day Yale comes to me and says, Guri, you use PowerPoint. But your slides also only have text. If you see somebody else's PowerPoint slide, they have all these fancy graphics and figures and so on like that. What's the use of using PowerPoint? Okay. I suspect Yale's PowerPoint slides also have text, and the figures they have are drawn by these special purpose PowerPoint units that are much more adept at using PowerPoint than Yale is, if you will. Okay, and that's fine. Okay, so what you want to have in these general purpose processing cores is you're going to be stripping out the stuff that you don't, that some other unit can do it for you. Okay, and so I don't know, Yale, do you know how to do figures in PowerPoint? I don't, so. AKA specialized figure drawing units. Okay, so when you have these specialized units, there is no reason for the general purpose core to be doing anything like that. Okay, so you know what we're going to have is you're going to have these dynamically specialized cores where the core will be either statically, you know, saying, hey, I'm only going to do OS code. I will never, this core will never do any OS code, for example. Okay, so I don't need to have any hardware support to doing anything that the OS might want done. No privileged instructions and the like. Okay, or I'm only going to run a subset of instructions on this code. You know, we sort of done that before, you know, but again, that has always been the exception. Now we are sort of going to want it to be the norm, if you will. Okay. Well, maybe I don't want to support precise interrupts in the core if I can somehow figure out how to do it some other way. Okay. So we're going to have many other forms, I believe, of limited functionality cores that you're going to use to not only reduce energy, but also improve performance. And how do you sort of improve performance and reduce energy in such entities is, you know, I think all of us understand that most processors today, how fast they execute and how energy efficient they carry out computation is all a function of how good their predictors are. Okay, so you know, now what we've been doing so far is, you know, I have a core with a set of predictors, and I'm dumping on that, you know, all sorts of different types of computations that's messing up the predictors. And if I just separate those computations out and ran each on different cores, the predictors would be in much better shape to carry out faster and more energy efficient computation. So what's likely to happen is what I see is a steady demultiplexing of what was done on that general purpose core. Okay. You're going to slowly start pulling it out. One of the proposals that we had several years ago that we call computation spreading, where we separate out the OS and user code into different cores, and then we dynamically switch between them as and when was possible. And we actually saw significant benefits, both in energy and time. And you can do that now because you have lots and lots of transistors and you don't know what else you may want to do with them, in some sense. Okay, so no need to keep dumping everything on that single core. You're going to separate the specific code to some form of accelerators, and you know, other forms you're going to sort of be stripping out. So what you'll be left with are cores that are mostly general purpose, if you will. Okay. So what you're going to have now is your hardware is going to look like a collection of multiple, mostly general purpose cores. And you're going to perhaps they may be further dynamically specialized to do only a certain form of computation. And you're going to have these special purpose processing, you know, hardware units of varieties of different flavors. And further, you're going to have more than you can power on at any given time. And so what's going to happen is your software is running and underlying the hardware is completely changing. Okay, and It'll all need to be transparent to the software. Okay. So what we need is we somehow need to come up with mechanisms to permit this, permit a diverse set of continuously changing hardware to be used, completely transparent to the software. And one of the questions that comes up that I feel is going to be important is just like once we had the notion of a precise interrupt, and you could put in speculation, and you could put in this prediction, you could put in that prediction, you could put in whatever you felt like completely transparently, okay? There will need to be some analog of a precise interrupt where that's going to be our mechanism to use to allow the software to think everything is good, but completely change it under the hood. Okay. So that's it. I think I've got us mostly back on time. Thank you. Pleasure being here.
Okay, we're actually going to have time for a break. There is a question, so we do have time for questions.
So we have lots of transistors to play with. You can certainly sync those transistors with computing energy, think bandwidths, atoms, whatever you like. But you can also sync them into memory. Right? And one might consider the idea of syncing them into memory whose purpose in life is to build online optimized code. Think about gym compilers. Okay? I can't imagine why it is we don't take the things that happen at runtime and analyze them much, much, much more deeply in the kinds of things that people try to do with conventional hardware. Transmitter guys look like they had a really good idea in the sense of taking this instruction set that wasn't right for what they wanted, looking at what happened and compiling it. What happens if you scale that up and use the transistors and build optimizers? Lots of code in your engine as opposed to dynamic function.
Are you with NVIDIA? No. We will see what happens in a few years on that one. So syncing them in memory, by the way, one thing, another area that is very ripe for innovation is what is the memory hierarchy? How is the memory hierarchy organized in a chip? And a lot of what's happened so far is we are taking things that we had from when we built multiprocessors, and we are using the same things in a sense with very little variations, whereas what we now have is we have complete control of everything inside, and that's room for innovation. Now, so re-optimizing code is interesting. You're using all these transistors for a problem which most software people are very happy to have a factor of 10 or 20 difference between their interpreted code. They're happy to go with the 20 times slower code as long as it improves efficiency. Are there not better uses for that? I got to believe there are better uses for those transistors, like, turning them on. I would probably even, rather than trying to optimize code, I would use them for tables, and try and use table lookup rather than computation, for example. There are many of the upcoming applications where you can do away the entire chunks of computation because they are doing the same computation on the same set of inputs repeatedly. So I would put them in table lookups.
So one comment I had is that I slightly disagree with you.
That's not new, Arvind. Yeah.
No, most of the things you were saying I'm completely in sync. You were saying it will be mostly general purpose cores and some, what we call them, energy efficient computing devices. I think it probably is going to be the other way around. That most of the things will be energy efficient.
Let me clarify that. I think you missed. When I said it was mostly general purpose, I didn't mean that most of the cores will be general purpose. I meant the general purpose core will, no, it won't be fully general purpose. It'll be general purpose enough.
Sure, I get it.
Okay. No, yeah, so you are running your 32-bit multiply on this core. Sorry, you can't do it. Do it on this other core.